So in this video clip, we're going to take a look at the American option valuation using binomial trees. We'll start off with the broad temple benchmark parameters and observe the estimated value of the option based on the stock price being $100, the exercise 100, the risk-free rate being 3%, the difference between the cost of carry. So that's the difference between the risk-free rate and the dividend being negative uh, 0.04. So that would be a dividend of 7%. So 0.03 minus 7 would yield 0.04 negative. Sigma is equal to 20%, T is equal to 3 years, and the step size is equal to 15,000 steps. So we know from Broad to Temple with a 15,000 step tree, the value of the option, the true value based on the 15,000 step is 9.066. If we come down first to our C++ code and run our code, so if we execute now to run the C++ code, this is again, the parameters are the same as the ones we had indicated at the beginning. And if we take a look here in the content folder, right, so I might just delete these out just so that we can see the pattern and how a little bit the mechanics of how C++ operates in Google Colab. So let's delete out those files. So if I run write file main.cpp, if we refresh the content folder, you'll note it'll come in here. We can double click and see the code is actually sitting there in the content folder. Then to execute that code, we follow by bash. So percentage script bash. And when we execute that, will take a second because it's 1,000 steps. Let's push up to 15,000. So at that level of accuracy is almost 9.066. If I push up to the 15,000 steps and execute again, we can see perhaps how our accuracy level might change. So it was 9.064. By pushing to 15,000 steps, we were getting out 9.0659 or 9.06, rounding to that number of decimal places, it would be 6. So comparing like against like, the value here we observe is the same as the value in our C++ code. C++ code has the great advantage of being extremely fast. So we're probably not going to beat the time performance here. Again, just so I can make the other snippets of code comparable, I'll change this down to 1,000 steps, execute again. And then when we look here, we see that the value is still 9.06. Well, it's gone down to 0.5, I guess. So a little bit of a trade-off in accuracy, but the time step is much reduced. So it's 0.04276 seconds. Or if we had written that in terms of milliseconds to compare below, it's about 42 milliseconds. If we run again, it's 39, not too different from here. So this 0.39644 corresponds here to 39.473 milliseconds. Okay, so the second snippet of code, if we come down, is I'm going to use again the Hogue mapping, and consistent with the C++ code, the array mapping takes this form. So these are our J's and I's. So it's like the step period, the J's, and then the I's give us where in the array the particular node is. So we know time step 1, 2, 3, 4. So 1 step, 2 step, 3 step, 4 step, and here 5 steps. Okay, so we have which step, the J is like the step, and the I then where in which node in that array. And for dynamic memory use, which we will use here in our C++ and binomial Python code, we estimate the arrays in sequence. So we don't estimate the entire tree at once. The values in the nodes pass. So we estimate the nodes in a given array, and then we pass back and go again. Okay, so that tends to improve speed performance. The first snippet of of Python code I'll use here follows the same architecture, and we use the same parameter inputs, but when we run the estimation, okay, it's the same value for the 1,000-step tree. We're getting the same estimation as for the C++ code, right? So just a quick check again to see that works. But where we may have an issue here is that the while the accuracy hasn't in any way been compromised, the speed at which the estimation is performed takes longer. So for the C++ code, where we observed that the number of milliseconds was about 39 milliseconds. But for our 0.03947 seconds, but for this first uh, snippet of Python code that we use, so if we come down, for this first snippet, the speed is equal to 1.46 seconds, right? Which is dramatically much higher, right? So to shave off some time, we can do some NumPy optimization and check again. And when we look here at the faster code, it does feel as if there's less latency. And we're back here to something like the 55, 68 milliseconds. So quite a difference in terms of the speed performance on the 1000 step tree. 1.46 seconds is 1,460 milliseconds, whereas with this optimized code, it's 58.8 milliseconds, so much faster. And then we can investigate the Cython code. So again, the same basic overall architecture in terms of the IJ mapping and dynamic memories being used again. But Cython has the benefit of being closer to C. So the speed performance here, if we take a look by inputting again the same parameter inputs as before and getting an output in terms of time, so same valuation and the number of seconds it's taken is very close to the C++ code. In fact, it might be better if we run that again. We might get a slightly different output. So again, it's 0.039. That's really fast. Let's put it up to the 15,000 seconds and just compare. Now, before previously, that took in excess of a second. Uh, it took 9 seconds, I think, with the C++. So here we have 8.3 for 15,000 step tree. Okay, let's run again. Just to observe Cython and how it compares to C. It compares favorably to C++ in terms of speed performance. And when we remove back to the 1,000 steps, so that's 8 seconds again, 0.035, so 35 milliseconds. So this is quite fast. We can run our results again and sample. So it's about again 33.4 milliseconds in terms of speed performance. And let's check again when we convert our code into same code, same binomial design, when we use Numba, another library, let's see if it's slower or faster this time compared to Cython. So using the same number of steps, same parameter inputs. So it's 1,000 steps, no, same accuracy and 5.2. So this really fast number here seems to, oh, for 1,000 steps, 5.2 seconds. Let's run that again. Okay, 0.042 seconds. So that's in or about the same time span it takes for the native C++ code and Cython perform. Let's run it one more time. 0.5, so 50 milliseconds, 0.7, 70 milliseconds. So quite a lot of variation here on the performance of Numba. Uh, would be a little bit slower perhaps than Cython and C++, but still quite a good performance and no compromise in terms of accuracy. Okay, so that's sort of an overview of speed performance with the different libraries, C++, Python using NumPy, Python using NumPy optimized, using Cython, and using Numba. We can see that the accuracy can be guaranteed, um, but speed performance is improved, right? In depending on uh, what we're using. So NumPy, Cython, Numba, and C++ are yielding similar levels of performance in terms of accuracy speed.